Hello everyone, welcome back. So in the last lecture we introduced the ideas of operators, and we also introduced the Hamiltonian for a quantum harmonic oscillator, right? So essentially what is the goal? We want to solve for the eigenvalues and eigenfunctions of the Hamiltonian, right? So for this, what are the eigenvalues and eigenfunctions? Why do we want that? Well, eigenvalues are the energies that are allowed for the system, and eigenfunctions are the wave functions, right? So we want to solve for that. So if you want to solve for that, you already know, right? I mean, what is the eigenvalues of a quantum harmonic oscillator? What is that? N plus half of h cross omega, correct. So basically we already told you the solution in the previous instances. When we talked about it, we said En is equal to n plus half h cross omega. And I said that, okay, let's not get into the proof of it, because if you want to really solve for it, if you take a, like a potential, right? Harmonic potential like this, in this potential form, if you take and try to solve it, it becomes very, very difficult. It's a parabolic potential, right? Potential energy is in the form of x square, so it will be some sort of a parabola like this, and if you want to exactly solve it, the solution is fairly complicated and mathematical. So we can't easily do that, but luckily for us, Dirac came up with a very simple algebraic way of solving for this. Okay, so using the operators that we just introduced. The idea was, if you have a Hamiltonian like this, I can try to rearrange it a little bit, and I will write it as this Hamiltonian. I'll write it as 1 over 2m. I'll take it out. Okay, then I can write it as px square, operator square, plus if I take out m, so basically m square omega square x square, x cap square. This is my Hamiltonian. So what Dirac, I mean, it's a intuitive thing, and it really is a reflection of Dirac's genius, that he said this more or less looks like, if you have x plus iy into x minus iy, I know that it is equal to x square plus y square. So what Dirac did was, he said, okay, this Hamiltonian looks like this. Let me factorize into two parts, which are symmetric. Okay, so what he did was, he introduced operators A and A dagger. Okay, we will talk about what these operators mean eventually, but he tried to look at this. So essentially he said, if you take a product of these two, okay, there's a h cross omega term. We'll explain why that comes. But essentially, if you take a 1 over square root of 2m into this value, I mean, this is basically x plus iy, and this is x minus iy, right? So if I take a product, I should get, p square plus m square omega square x square. So that's what I would expect if I factorize it. Okay, so he tried to take this approach. He defined these operators. We have this additional h cross omega because it makes overall, the solution simpler. That's why it is there. Okay, so now to solve for this, we will just use the basic operator algebra that we just learned. Okay, so the first thing we will do is, let's take and compute a cap a dagger. Okay, what is this equal to? Okay, how do we compute that? And first of all, we should be careful with operators because they don't commute. We have seen that with x and p previously, right? So we will take step by step and do it. Okay, so now this is going to be 1 over 2m h cross omega, because both have a under root of 2m h cross omega, into m omega x cap plus I px x cap into m omega x cap minus I px x cap. Okay, so if you ask me why this form and all that, I will not be able to give you any answer, satisfactory answer. It's just that if you have this form, it turns out to be very simple, just like what we did with generalized momentum and generalized position and all that, right? So there's a lot of my brilliant minds that looked at it for a long time, and then they came up with these things. Okay, so now what happens if you have a product like this? So well, we'll just keep this 1 over 2m h cross omega into m omega m square omega square x cap square, correct? Plus m omega, so minus it will come. So minus, okay, let me take just the squares first. It will make our life simple. So plus px square operator, this is the Hamiltonian part, right? But in addition, you also have these other terms minus I m omega x cap p cap minus, so plus I m omega px x cap. This is what I have. Okay. Now, just remember that you can't cancel these two because x and p do not commute. Correct? So when x and p do not commute, what do we get? So this I can further simplify it as 1 over 2m h cross omega into m square omega square x cap square plus px square minus I m omega into x cap p cap minus p cap x cap. Correct? This is what I have. So that's going to be equal to 1 by 2m h cross omega m square omega square x cap square plus px square minus I m omega. I know this is IH cross, right? So IH cross, correct? So then effectively this is coming out h cross omega. If you take out, or rather if this will simplify to 1 over 2m h cross omega, or rather let's take it inside. Let's make our life a little simpler. Let's take it inside. If I take it inside, or let me do this. I'll take only the 2m part inside. I'll take 2m part inside. So if I do that, 1 over h cross omega into 1 over, this is px square by 2m plus half m omega square x cap square. This is my IH cross I and minus y. So basically plus, I took 2m inside, right? So h cross omega by 2. Okay, this is what I have, right? Did you get the same answer? So basically you have the Hamiltonian plus h cross omega by 2. There's a h cross omega outside, right? So this is the first one that this is the solution you should get. Yeah, we got that. Now let's see what happens if you do the other one. Okay, what happens if you try A dagger A? Okay, if I want to try A dagger A, I'll get 1 over 2m h cross omega into, now A dagger means the definition is basically m omega x cap minus, right? So m omega x cap minus p x cap ipx cap into m omega x cap plus ipx cap. Okay, the same thing goes. So now we'll keep this 2m h cross omega into m square omega square x cap square plus px square minus, no, plus now m omega I m omega x cap px cap minus I m omega px cap x cap. Okay, if I do the same thing and I take my, let's say, same solution, I take 2m inside, or rather, okay, 1 by 2m h cross omega into m square omega square x cap square plus px square plus I m omega into I h bar. Correct? So you'll quickly see that if I do this 1 by h cross omega into px square by 2m plus half m omega square x cap square. Okay. Plus half, no, not plus half. This should be a minus half here, not a plus half. Minus half h cross omega. The previous term had essentially h cross plus half h cross omega, Hamiltonian plus half h cross omega. Now we'll get minus half h cross omega. Okay. Now the question will be, what is the commutator bracket of A dagger? That's going to be equal to A dagger minus A dagger A. So the whole terms, basically if you have these two terms, the first expression here, number 1, and this is number 2, both of them, you subtract each other, you essentially end up with 1 by h cross omega into half h cross omega plus half h cross omega. Okay, so the commutator bracket A dagger A or A dagger is going to be equal to 1. This one. We will discuss the implications a little later. We're just establishing the rules of the algebra right now. Okay, you can also write it in another form. You can say that A dagger is going to be equal to 1 plus A dagger A. Okay. Any problems? No, I would strongly, I think here if you have the live students who are actually working it, and I would strongly advise you to actually do that as well so that you get familiarity. This thing cannot be done by just seeing. Okay, we'll have to work through it once. A dagger will be plus half h cross omega. Plus half h cross omega minus will be there. Hamiltonian expression minus will be there. Okay. You there it? Right? So we'll just discuss the implications again, in the next lecture. I want to just establish the algebra. Okay, why this means all that, because we'll start using these terms and then we'll explain, how this will be helpful. So these are essentially operators that you will find, in any quantum optics related work, you will talk of operators like this. Okay. So if you have such a scenario, now okay. So now essentially we are ending up with these expressions, and we also said that A dagger, the bracket, commutator bracket A dagger is going to be equal to 1. Okay. Now we'll just do one thing. Okay. If you look at it, we recognize that this term is effectively like the Hamiltonian, right? M omega square x square. So what I'll do is I'll write this. Okay. So I will rearrange it and write in terms of Hamiltonian H. Okay. Hamiltonian H is going to be equal to P square by 2m plus half m omega square x square, and that is also going to be equal to h cross omega will go there. So h cross omega a dagger minus half h cross omega. Correct? So that is equal to h cross omega, if I take out common, a dagger minus half. This is using 1. 2 implies, this is, I'll call it as 1 and this is, I'll call it as 2. 2 implies h cap equal to same px square by 2m plus half m omega square x cap square equal to h cross omega a dagger a plus half h cross omega. That's going to be equal to h cross a dagger a plus half. Just take a few moments and yeah. Basically, we are writing Hamiltonian in terms of a dagger minus half and a dagger a plus half. That's it. Okay. The last thing we will try. If you want, just pause the video a little bit for the online audience, and then you can actually work it out and then come back to it. Okay. Okay. So now what we have done is we have introduced this idea of commutator bracket for a and a dagger, and then we got an expression for the Hamiltonian in terms of a dagger a and also a dagger, that is also equal to half a dagger minus half. We got this. Now what is the commutation relation between h and a? Okay, how do we find out this? H and a, if I want to find out, I'll say h is going to be my a dagger minus half into h cross omega, right, comma a, isn't it? And that will turn out to be equal to, if I take out, or we can expand this, this is going to be h cross omega everywhere into a dagger. Okay, let me drop the hats, okay, but they're all there. I mean, they're all operators. A dagger a minus a by 2, correct? I'm using a dagger minus half. Now if I do that, yeah, I'll get a dagger no, but a by 2 will be there and then a by 2 will be there. So now what will happen is opposite, right? So a directly product and then now opposite a dagger, and then there will be half again, correct? This will be plus half or plus a by 2. If I do this, effectively I'm getting h cross omega into, I can take out a and then I'll get a dagger a minus a dagger. Okay, so that will turn out to be equal to minus h cross omega a. Okay, if I take a commutator bracket of h and a, I'll get minus h cross omega a. And similarly, if I take commutator bracket of a dagger, I can show that it will be h cross omega a dagger. Okay, I think you should get more or less the same thing, right? So basically you will get, if I take commutator bracket of h and a, I'll get minus h cross omega a. If it a means, I'll get plus h cross omega. Now the question is, what does it mean? Okay, we will actually try to see the implications. Okay, so if you look at h cross omega, let's say I'll take h and Hamiltonian h a dagger acting on a wave function psi. What would it be? Well, okay, let me do this. I'll stop here. I'll introduce in the next lecture. I'll actually look at what happens to energy eigenvalues once you apply. So in this lecture, essentially we have introduced the eigenvalues, or rather the operators, and how they behave. Okay. So I want you to remember essentially 3 points, or rather whatever is summarized here, right? So the commutator relation between A and A dagger is going to be 1. H can be written in both of, A dagger A and A dagger. And if you take a commutator bracket of H and A, you get minus H cross omega. And if you take H A dagger, you get H cross omega. So these are the 4 relations that I want you to remember. Okay. Because we will use it and we will talk about what are the implications of this. So to summarize, what I did in this lecture was I introduced the idea that if you want to solve this Hamiltonian, there are the actual, the numerical way of, writing the differential equations and solving it is going to be quite challenging. So Dirac introduced this idea of using operators, and wherein he simply tried to factorize the Hamiltonian in terms of 2 operators, A and A dagger. We will talk about what the meaning of these operators is in the next lecture. But for now, if you accept these definitions and go through the algebra, you will see that A and A dagger, of course, don't commute. Okay, the first thing. Basically, their commutation relation, if you they'll actually have, if you take a commutator bracket of them, it will turn out to be 1. Okay, and then Hamiltonian can be expressed in terms of both A dagger A and A dagger, and then finally, your the Hamiltonian, if you take a commutator bracket with A, you will get minus H cross omega. If you take it with A dagger, you will get plus H cross omega. So H cross omega A dagger. Okay. So these are the results that I want you to just remember or recollect, or work it out rather. Okay. Not remember, work it out. And then in the next lecture, we will use all of this to actually look at how the energy eigenvalues of a quantum harmonic oscillator behave. All right. So with that, I'll stop. Thank you so much for your attention, and we'll see you in the next lecture.